Welcome to Lecture 34, the first of several lectures on magnetism. Magnetism is something you're familiar with. You use magnets in everyday applications like, for example, sticking things to your refrigerator. I just grabbed this magnet off a refrigerator. But you know of magnets perhaps as things also that can pick up iron objects. There's an attractive force between the magnet and iron. You know that magnets have two poles. This happens to be the north pole of the magnet, the one that's labeled red, and north poles repel each other, and south poles repel each other, and north attracts south, and south attracts north, and so on. You know that magnetic compasses work by magnetism, and I have some magnetic compasses here on the table, and if I move this magnet around near them, you can see the compass needles responding to something that this magnet is creating in the vicinity of the region around it. Here's a device that consists of a number of small magnetized pieces of iron mounted on a pivot. If I put a piece of magnet on them, you get a characteristic pattern that you've probably seen when maybe your teacher in elementary school sprinkled iron filings near a magnet, and they formed in this characteristic pattern, which, by the way, looks very similar to the pattern we saw for the electric field of an electric dipole. In fact, we can define the magnetic field by doing experiments like this and talking about the little local direction that a small compass-like needle would take. And if we draw a little line in that direction, that's the direction of the local magnetic field. And if we then move to a different point and look at the direction there, we can find a different direction for the magnetic field, and that way we can trace out what are called magnetic field lines. In fact, with this big magnet here, I've got a small device that has a tiny magnet mounted in a gimbal. It looks exactly like the big magnet. It's gray with a red end, and it can pivot in any direction. And as I move it around, it points in different directions, and I could use those directions to map out a magnetic field line. In fact, it would look sort of like the field line of a dipole. So this little probe would allow me to trace out magnetic fields. So we have at least an operational definition of what I'm going to call a magnetic field. And that's probably as far as we can go with your familiar understanding of magnetism, because you probably think of magnetism as something having to do with these unusual objects we call magnets, and you know it also has something to do with a relatively small class of materials that include iron and steel and a few other materials that may be less familiar. It does not include other common metals like aluminum or copper. They aren't affected at all by magnets. So magnetism seems to be a relatively obscure small thing. But that's not, in fact, the case. That's not what magnetism is about. Magnetism is about something very different, and I'm going to leave magnets aside for a while. We'll get back to them much later and understand more what they're about and how they fit into the bigger picture. But the big picture of magnetism is very different, because the big picture of magnetism is this. What magnetism is really about, I'm going to say it big and I'm going to say it loud, magnetism is about moving electric charge. Magnetism is about electricity just as much as everything we've done so far in our lectures on electromagnetism have been about electricity, because magnetism is fundamentally a phenomenon involving moving electric charge. It's moving electric charges that respond to magnetism, and it's moving electric charges that cause magnetic fields. And we want to spend most of this lecture exploring the first half of that, how moving electric charge responds to magnetic fields. Then in the next lecture, we'll look at the second part where moving charge causes magnetic fields. So let me give you one demonstration of that. Here's an old-fashioned cathode ray tube television. There probably aren't very many of these left in the world. They worked by shooting a beam of electrons from in back of the TV. That's why they had to be so thick, toward this screen, and when they hit the screen lights up, and by aiming the beam and changing its strength and so on, you could paint a picture on the screen. We don't have a picture on the screen because we don't have an antenna connected. But there are beams of electrons coming, making the patterns on that screen, and I'm going to turn on the volume setting just so I can have something to see. And then I'm going to take another big magnet and hold it near this television. You can already see, by the way, there's some funny lines on that screen, but I'm going to turn this on, and those electrons, which are coming toward the front of the screen, are now dramatically affected, as you can see, by the magnetic field of this magnet. And that's a clear demonstration that the moving electric charges, those electrons that are beaming through the empty space in that cathode ray tube toward the front of the TV, that they're being affected by a force. And that's the magnetic force, and we now want to spend some time exploring that magnetic force. So let's look at magnetic field and magnetic force. First of all, I want to look at the magnitude of the magnetic force. The magnetic force, again, acts on moving charged particles because what magnetism is about is moving charged particles. Moving is emphasized there. Charged particles at rest, they don't feel magnetism, but when they move, they do. And they feel a force that's proportional to the charge, Q, electric charge, and magnetic field strength, which I'm going to call B with the symbol B. So that's familiar from electricity. The electric force on a charge was Q times E. But there's more involved here because it also depends on the charge velocity v. And v is a vector. It has direction as well as magnitude. And it's proportional in particular to the magnitude of the velocity times the sine of the angle between the velocity and the magnetic field. So the magnetic force is more complicated to think about because it involves thinking about the direction of the velocity in relation to the field. In particular, if the velocity were right along the field, if a charged particle is moving parallel to a magnetic field, no matter how strong the field is, it would experience no force because sine theta would be 0. The magnitude of this force is QVB, the product of those three things that count, the charge, the velocity, the magnetic field, and also that directional factor, sine of theta. The unit of magnetic field, if you work that all out, is Newton seconds per Coulomb meter. That's given the name Tesla after Nikola Tesla, a Serbian-American inventor who did all kinds of interesting things in his life. 1 Tesla is actually quite a strong magnetic field, so you'll often hear magnetic fields expressed in Gauss, and a Gauss is a 10,000th of a Tesla. Now that's the magnitude of the magnetic force. Let's talk about the direction of the magnetic force, which again acts on moving charged particles. And the direction of the force turns out to be perpendicular to both the velocity and the magnetic field. Those are both vectors, and they have direction, and the direction of the force is perpendicular to both of them. So there's a rule, and the rule says take your right hand, as this picture shows, and curl it in the direction that would rotate V onto B. And that is almost the direction of the magnetic force. Let me do an experiment here. So here's V. We've been using blue for velocity. Here's B. We've been going to use purplish color for magnetic fields. And if I want to know the direction of the force on a charged particle moving with that velocity in a magnetic field pointing this way, I try to rotate that velocity arrow till it lies on top of the magnetic field arrow. And I curl the fingers of my right hand in the direction that would do that. So that's like that. And my thumb points in the direction of the magnetic field. In this case, it's straight toward me. If it were the other way, I would go, and there it goes, and the magnetic force would be outward. Now, be a little bit careful. Because the magnetic force involves the charge Q, that direction that your thumb points is the direction the magnetic force would be on a positive charge. The minus sign of a negative charge means the direction would be opposite for the opposite kind of charge. So that is how we actually calculate the magnetic force on a moving charged particle. If you want to get it mathematically, we have this shorthand that says the vector force is Q times the vector velocity with this big fancy multiplication sign that's a kind of way of multiplying two vectors together that encapsulates the meaning of both QVB sine of theta and also this directionality by that so-called right-hand rule. So that's how we calculate magnetic forces. Let's do an example of one important application where the magnetic force becomes significant in a number of different kinds of technological and natural applications. It's called cyclotron motion. So I'm going to imagine here that I have a magnetic field that is pointing out of the screen. And as soon as I start talking about magnetism, things get complicated because I really have to work in 3 dimensions. So on a 2-dimensional screen, I show a magnetic field coming out with a dot. Think of the dot as the arrowhead. If I showed a magnetic field line going in, you'd see a kind of cross showing the tail of the arrow. So there's a magnetic field pointing out. There's a charged particle with a positive charge moving here to the right with some velocity v. What happens? Well, I do my right-hand rule. I say I got to rotate v onto b. B is out. I've got to go that way. So I curl my right hand in the direction that would do that, and the magnetic force is down. So the magnetic force has magnitude QVB. Its direction is perpendicular to both V and B, and by the right-hand rule, we've just seen that it is pointing downward. So there's a force at right angles to the velocity. Now remember, way back from mechanics, that forces that act at right angles to a velocity change only direction and not magnitude. So a little while later, this velocity is going to have had its direction changed, but its magnitude is going to be the same. So it changes the direction, not the magnitude of the velocity, and later the charged particle will be moving with the same speed, that is the same magnitude of its velocity, but in a different direction. And if you compute the direction or figure out with the right-hand rule the direction of the force, in that case, you will find, once again, that if I take V now this way and I rotate it onto B, I've got to get my right hand in the right configuration to do that, I get a force down in that direction. And this process continues with the velocity changing in direction, but the speed not changing. And so we go continually around like that. Same idea, same force, because the magnitude is still QVB and V hasn't changed. The direction of the velocity has changed, but the magnitude hasn't. And you get the picture. The result of that kind of motion, a force that remains constant in magnitude, but whose direction is always perpendicular to the velocity, produces, as we've seen way back in earlier mechanics lectures, that produces uniform circular motion. So there is circular motion here, and that charged particle will just continue to go spiraling around or circling around in that magnetic field. Let's be a little more specific about that. If we apply Newton's second law says the force, magnetic force, any kind of force, is ma. The acceleration we know in circular motion back from lecture 6 is a equals v squared over r. Put those two together, qvb is mv squared over r. F equals ma. Do a little algebra on that. You can solve for the radius. It's mv over qb. And let's continue that calculation. We've got the radius of this path. Depends on the mass of the particle, the velocity of the particle, speed of the particle, the charge on the particle, and the magnetic field. Let's relate velocity and radius and period. Velocity is distance over time. 2 pi r is the circumference of this circle, divided by the period, the time it takes to go around, t. And we can rewrite r as m times the velocity over qb, the velocity being 2 pi r over t. Do a little algebra. The time is 2 pi m over qb. That's called the cyclotron period. If we take its inverse, we get the cyclotron frequency 1 over it, which is the number of circles it makes per unit time per second in the SI system. And here is the really neat thing about this, that cyclotron frequency and the period are independent of the radius, the speed, or for that matter, the particle's energy. You put a particle with a given charge and mass in a magnetic field, and it's going to undergo circular motion, and the period and frequency of that motion do not depend on anything but the properties of the particle and the strength of the magnetic field. So that's cyclotron motion. Remarkable, simple idea there. By the way, I have to say that idea only holds for velocities that are low compared to the speed of light. Relativity comes in and negates this conclusion at very high speeds, but at reasonably low speeds and low energies, the period and frequency of this motion are completely independent of the particle's energy. So that is a remarkable result. And let's take that result and look at some applications of this cyclotron motion. So one application is the device for which this thing is named, a cyclotron particle accelerator. In a cyclotron particle accelerator, particles, protons, nuclei of various atoms are accelerated in ever-enlarged spiral paths. They're given energy by an electric field, but they're held in place by a magnetic field. And as their path spirals ever larger, the frequency, the rate, the number of turns they make in a unit time, or the time it takes to go around, doesn't change, as we just saw. And so that makes it very easy to keep the whole thing in synchronism. So there's a little diagram of a cyclotron, and on the right you see an early medical cyclotron that was actually used in developing the procedure we now call PET scanning. In your microwave oven, there's a special tube called a magnetron that has permanent magnets, and electrons spiral around in the magnetic field of that magnet, and they generate the microwaves that then cook your food. We use cyclotron motion to heat plasmas when we're trying to make fusion happen here on Earth. And finally, astrophysicists can use this process to measure astrophysical magnetic fields, because if they see some emission of electromagnetic waves that's coming from, they know electrons moving in some region, and the region probably has a magnetic field. From the frequency, they can immediately calculate the magnetic field strength. So there are a lot of applications of cyclotron motion, both in practical technological devices as well as in nature. Okay, now the picture I used to talk about cyclotron motion and to derive the cyclotron period and frequency was on the big flat screen, and the motion of the charged particle was simply in 2 dimensions. It was moving on that flat screen. What happens if 3 dimensions are involved? Well, it's not much more difficult because remember that there is no magnetic force on a charged particle if it's moving along the magnetic field. So if I give that particle that was moving in a circular path perpendicular to the magnetic field, if I give it a component of motion along the magnetic field, that component won't feel any force. And what the charged particle will do is simply spiral around the magnetic field line, moving in the direction it's going. And that's a very important process in a lot of situations, particularly in astrophysics. And here's a beautiful picture I've showed you before. This is of the sun's outer atmosphere, the sun's corona, and that loop-like structure you see actually consists of charged particles, mostly electrons, spiraling rapidly around the magnetic field line. And so they're tracing an actual picture of a magnetic field line on the sun, and that is what happens in 3 dimensions. These charged particles spiral back and forth. Another example, in Earth's magnetic field, which looks sort of like a dipolar field, more on that later, charged particles spiral around along those magnetic field lines, and you can see the magnetic field lines come down to Earth near the poles, and that's why high-energy charged particles from the sun, for example, that get trapped in the Earth's magnetic field, cause the auroras as they barrel into the atmosphere in the polar regions of the planet. Okay, well, let's move on to some technological aspects of magnetic fields and moving charges, because one of the most important kinds of moving charges is a current. We've talked about currents before, flows of currents, electric circuits. Let's talk about the magnetic force on a moving charge in a current. So here's a simple example of a current, a bunch of positive charges moving to the right. If there is a magnetic field present, and here I've drawn the magnetic field going into the screen, you can do the right-hand rule on the velocity to the right, the charge carrier motions to the right, the magnetic field is into the screen, and you'll find that the force on those charge carriers is upward. So a flowing current gets magnetic forces on its individual charge carriers. It doesn't really matter what the sign is. If the charge is being carried, the current is being carried by electrons moving to the left, they nevertheless constitute a current moving to the right, and that current moving to the right still experiences a force upward. The velocity is in the opposite direction. V has the opposite sign, but so does Q, and in the magnetic force, the direction is still positive, so the sign doesn't matter. It's actually a little bit more subtle than that. What actually happens in typical metallic wires is we have the positive charges at rest. They're the ions, the backdrop of atoms making up the material. They don't feel a magnetic force. The electrons do feel a magnetic force. They're deflected to one side of the wire, and then that develops an electric field between the negative and positive, and the electric field pulls the rest of the wire along with it. So the so-called magnetic force on a current-carrying wire is actually a little bit more subtle, and it involves both magnetic and electrical interactions. There's the upward force on the electrons, and then that the magnetic force, and then that gives this electric force on the ions. So things are a little bit more subtle than purely magnetic forces. If we have a long straight wire, and you work out, in fact, what happens to the magnetic force on the individual charge carriers, I'm not going to go through the mathematics of it, but it turns out that if the wire is oriented perpendicular to a magnetic field, as in this picture, the force is simply the current times the length of the wire times the strength of the magnetic field. If it's oriented at some other angle, there's a sine theta in there. But the important fact about this is it doesn't matter how fast the individual charge carriers are going or what their charge is. All that matters is their product, and that's what makes up the current. And so it doesn't matter whether it's a few charge carriers moving fast or a lot of them moving slowly. The magnetic force on a conducting wire turns out to depend only on the current and the length of the wire and the magnetic field. Let's do some demonstrations of that. So over here, I have a demonstration in which I've simply got a piece of conductor. It happens to be a piece of aluminum foil because I wanted something fairly light. It's connected to a power supply. It's going to send current up here and down through the wire and back to the power supply. And this is a hefty power supply capable of supplying 10 amperes of current. So I'm going to turn the power supply on. You don't see anything. The aluminum is actually getting a little bit warm nevertheless. And now I'm going to move the magnet near the aluminum foil. And you can see that repulsive force. Well, it's not exactly repulsive. It's sort of sideways, in fact. And that's that funny right-hand rule business of the magnetic force. The magnetic force the magnet is not repelling that. It's pushing it sideways. And if I turn the magnet around, it's pushing it sideways the other way. So there's an interaction. Now remember, aluminum is completely non-magnetic. Aluminum is not a magnetic material. And nevertheless, there's an interaction here, and it's the interaction with the moving charges in the current-carrying aluminum. Here's another example We have here a light bulb with a vertical filament, and I've got it kind of dimmed down so you can see it without it being too glaring. And there's current flowing through that, and this is connected, plugged into the standard AC power, which oscillates 60 times a second. And so if I put a magnet near that, the filament goes into oscillations, and you can see that in the form of sort of standing waves on the filament. As I move it up and down, different segments of it get into bigger oscillations. And that's because the magnetic force is constantly changing direction because the current is alternating 60 times a second. So there are two examples where currents in magnetic fields experience forces. Okay, so now let's look at a really important practical application of this phenomenon of forces on current-carrying wires. What I have here is a rectangular loop of conducting material, and I'm going to imagine there's a current flowing in it down this way, up this way, and I'm going to ask what happens if I put this current-carrying loop in a magnetic field pointing to my left, to your right. So let's turn on our virtual magnetic field here, nice uniform magnetic field pointing to my left, to your right, and we'll ask what happens to this current loop in that magnetic field. And let's focus particularly on this side of the current loop where current is flowing upward. Now, we know how to do the right-hand rule. The right-hand rule says the way to figure out the direction of the magnetic force on a current is to rotate the current. Rotate the current or the velocity of the charged particle, same thing, into the direction of the magnetic field. So that would be taking this vertically oriented piece and rotating it like that, and that tells me the magnetic force on the vertical rising part of this loop is toward me, back, away from the screen. Now let's ask about what happens over on this side. Well, everything is the same on this side. The magnetic field strength is the same. The magnitude of the current is the same. The length of the piece is the same because I've got a rectangular loop. But the direction of the current is opposite, and therefore the force is the opposite, and the force is out. Now the force has the same magnitude outward there as it does inward here, and so there's no net force on the loop. So the loop isn't going to go anywhere. But what the loop is going to do is experience a torque that's going to tend to pivot it and align it with the magnetic field, or align the loop plane so it's perpendicular to the field. The perpendicular to the loop is then oriented with the magnetic field. That's what happens to current loops in magnetic fields. It doesn't matter whether they're current loops like this one made of wire or atomic current loops made by charged particles circling around in atoms. Current loops tend to align themselves with magnetic fields in this sense. Let's turn off the virtual magnetic field and talk a little bit more technically about this. We define the loop to have a magnetic moment vector, it's called. And the magnetic moment vector is a vector perpendicular to the loop area, and its magnitude, mu, the Greek mu, is the current in the loop times the area of the loop, and this turns out to be true for any loop shape. And there's a torque on the loop, and the torque rotates the loop into alignment with the field, and the torque is the magnetic moment, which depends on the current and the area, the magnetic field strength, and then this factor sine theta, where theta is the angle shown in the picture that determines whether the system is out of or in alignment with the field. And when it lines up completely, so the magnetic moment is aligned with the field, then there's no more torque, and then the loop sits in its position from then on. Okay, well, that doesn't sound very useful, because what we can do is rotate a loop until it does that. But with a clever change in the direction of the current, we can keep it rotating and we can make an electric motor. And let's look at how that works. So what an electric motor is basically a current loop that's placed in a magnetic field, typically between the poles of a permanent magnet or maybe an electromagnet, so we can do it either way. And that loop rotates. It's on some kind of bearings on a shaft. And here's the really clever thing. Toward the left there, you see a battery connected to this structure. But of course, the battery's stationary and this loop is rotating, so we somehow got to get the current in there. So we have these little semicircular rotating copper or other metal pieces, and we have things called brushes, which are typically made of wire or carbon, and they're contacting those rotating surfaces, and they're letting electricity flow through. And here's the really clever thing. That connection is called the commutator, and you see a little gap there in the commutator. And what happens is, as the loop rotates, it would normally just align itself with the magnetic field, as we've just seen. But just as it gets near alignment, that commutator switches past that gap, and that reverses which part of the battery is connected to which part of the loop, and that reverses the direction of the current in the loop, and that means the loop is no longer in alignment with the field. In fact, it's out of alignment, and it wants to rotate a whole 180 degrees to get back into alignment. And so it tries to do so, but just as it barely gets there, the commutator reverses the direction of the current again, and the loop just keeps rotating around. And that is an electric motor. And electric motors are vital, important, ubiquitous things in our society. Before we talk about that, let me demonstrate how an electric motor works. So here I have a very simple demonstration electric motor. It consists of a coil of wire. You can see the coil of wire. There's many, many turns of copper wire on there. It's on a rotatable shaft. There are magnet pole pieces attached to the sides of the motor structure. And there's actually a permanent magnet down the middle of it also, so it sits basically permanently aligned to that magnet. If I turn it, it swings back. But now I'm going to attach electrodes. I'm going to attach a battery to these two contacts, and those contacts are connected to these metal pieces that are rubbing against the commutator, the part where there are the two rotating contacts that connect to the coil of wire and let current pass through it. So let me make that connection. So I'll take the positive and I'll put it over here in that hole. It's then going into that terminal and into the brushes and into the coil. And I'll put the negative here, and I've got to give this particular motor a little spin, although a practical motor would be designed to do this automatically. And there it goes. And it keeps rotating. Take the battery away, it stops rotating. Put the battery back on and give it a spin, it rotates. What if I reverse the direction of the current? And there it goes in the opposite direction. So I have a direct current motor. It runs off this battery, and it does so by cleverly reversing the direction of the current and making a torque on a current loop. So there's an electric motor, very simple example of one, but electric motors really are ubiquitous and vital to modern society. Here's some pictures of electric motors. There are big industrial motors that operate all kinds of machinery and industrial processes. There are tiny little miniature motors. There's a motor that runs a hard disk drive in your computer, spins it at typically 7,200 revolutions per minute. There's a electrically assisted bicycle with a little electric motor mounted in its rear hub. There is the motor in a Toyota Prius hybrid. That motor is got about 50 or 60 kilowatts of power. It's almost as powerful as the gasoline engine, and it drives the car when the battery is fully charged and the car is starting up and the electric motor, the gasoline engine doesn't need to be on. And there is a common everyday workhorse motor that occurs in your washing machine. It moves the agitator back and forth or spins the drum in a vertically front-loading washer and also makes it go into high-speed spin and so on. So motors are everywhere. There's electric motors in almost anything, from subway trains down to tiny sub-miniature devices, electronic devices, and so on. Electric motors are ubiquitous, and they work on the principle, the basic fundamental principle, that magnetism is about moving electric charge, and the moving electric charge in the current loops of the electric motors are what give rise to these torques that keep the motor spinning. So let's summarize what we know in this first lecture on magnetism. The big idea, the thing you should remember 10 years out from this course, if you've forgotten everything else, is that magnetism is really about moving electric charge. The magnetic force on a moving charge depends on the charge, it depends on the magnetic field strength, and it depends on the charge's velocity by this complicated geometrical relationship that we can sum up in that simple mathematical statement I've written there. Charges undergo circular, or if they're moving in 3 dimensions, spiral motion in uniform magnetic fields. The forces on electric currents result in torques that tend to align current loops with magnetic fields, and that's what gives rise to electric motors. So that's a mouthful about magnetism, but the big idea is magnetism involves moving electric charge.